Okay, Algebra 1, this is the second part of the video lesson about Chapter 3.5. In the first part, we talked about two other techniques for solving word problems. One of the strategies was to make a drawing, the other was to use a table. Here we're going to talk about the third strategy, which is using a graph. But we're actually going to pick up with the last problem that we were talking about in the previous video. Here is that problem where we were talking about comparing cassette player sales and CD player sales, and we found that in year 4 the two amounts would match, and we found that by using a table. But we're going to convert this data to a graph. So here's that same table, and in order to make a graph of this, I felt it was necessary to make a broken graph to fit everything on here, and even then I had to squeeze things on. I have to admit that sometimes I take more than one try. This was probably at least 2 tries, maybe more, to get this to fit properly, but I finally was able to fit everything on here the way I wanted to. So I've got years along the bottom. After all, years are going to be my independent variable, and the number of players that I sell are going to depend or be a function of the number of years that go by. So I've got the number of players on my y-axis where they belong. And I had to have a broken graph so that I could fit from 200 all the way past 600. So from here I simply plot the points that I have on this graph. So for example, one of my points is going to be 0, 640. And that's this point right here. In the year 0 I've got 640 cassette players. In the year 1 I've got 570, that's this point. In the year 2 I've got 500 cassette players, that's this point, and so on down the line. Similarly, I've got the set of green data that I've labeled it here, the CD player sales. In year 0, I sold 200 CD players, so there's that dot. In year 1, I sold 240. In year 2, 280. There's 2 and 280, and so on this way. And notice that this yellow path and the green path cross each other right here, which shouldn't surprise you. That crossing point right there, that is that 360 value that we said would happen in year 4. The nice thing about a graph is that crossing points like these, like this one, really jump out at you in a graph. It's not so easy as you read through a table to find, oh, there it is. There the numbers match. But it's immediately visible as soon as you look at the graph. And that's one of the reasons that we do end up using graphs. So I want you to do the same thing. I know that you've seen, if you were in class, I know that you've seen already this question here, but I want you this time to go a step farther if you did do it, and most of you didn't. But either way, I want you to go a step farther, and I want you to make a graph that shows where the two cities have the same temperature. So first of all, you're going to end up wanting to make a table, and then once you have the table, you're going to want to make a graph from that. So go ahead and hit the pause button, get as far as you can, and then come back, and I'll work through it with you if you haven't finished it. Okay, I'm going to assume that you paused, you worked as far as you could, and you've come back to see what I ended up with. Well, first of all, here's the table that I created. In hour, instead of year this time, in hour 0, Detroit's temperature was 69 and Atlanta's was 84. But Atlanta goes down by 3 degrees every hour. Each time it goes down 3 degrees, while Detroit goes up by 2 degrees every hour. If you do this, you'll find in the table that you don't need to go past hour 3. I gave myself room to allow for 5 hours and filled it out for Detroit, but I found that they had the same temperature by year 3. So the next part of the task is to go from there, where I have this table, to create a graph like this one. I made Detroit yellow, and the starting temperature for Detroit was 69 degrees. There's 69. I made Atlanta green, and its starting temperature was 84, which is right here. Atlanta's temperature is going down by 3 degrees every hour, and that's what this path shows. and Detroit's is going up by 2 degrees every hour, and that's what this shows, and they cross, and like I said before, it really jumps out at you on a graph, they cross right here at hour 3 at 75 degrees. And that's also what appears in the table, but it just doesn't become something that's immediately as obvious. Okay, the textbook uses example 3 to teach this lesson. I think example 3 is a more complicated example, and I want to work through this one with you. Go ahead first, hit the pause button, read the paragraph, and make sure you understand what they're talking about. Okay, I'm going to assume that you've done that and that at this point you could understand the table that would be set up from this. Here is the frame of that table. As seconds go by, the count will be for how far the gazelle ran and how far the cheetah ran. This time, though, it is a bit different because this time it's not that they start out at the same place, it's that they end up at the same place. Well, actually, if you're the gazelle, you hope they don't. If you're the cheetah, you hope they do, of course. It's dinner. So I've run this problem as though we're looking at it from the cheetah's perspective. The cheetah wants to reach the gazelle by the 20th second because, as it says, after 20 seconds, the cheetah's worn out. So it's only going to run for that long. So the way I did this problem is I filled out this table for the cheetah first. At the starting point, the cheetah hadn't gone anywhere. Now notice, I ended up deciding I'm really not going to fit a table with 20 columns on this screen. So I thought of going by every 2, but even that wasn't going to fit. So ultimately I went by every 4. And I'm sorry that this table is a little bit confusing. Yours might be a little clearer for you. But after 2 seconds, you go 2 times 88 feet. Remember, it's 88 feet per second, so twice that is 176. That's how far the cheetah runs in 2 seconds. So in 4 seconds, it's 4 times 88, or in other words, 352. In 8 seconds, it's 8 times 88. So continuing to fill this out here, after 20 seconds, it's 20 times 88 feet, or in other words, 1,760 feet. That's how far the cheetah can run before it gets worn out. So for the gazelle to be caught right at the 20th second, it would be at 1,760 feet after 20 seconds. Now here, I did this problem completely differently from the way the textbook did, and we'll talk about why in class. But I decided, okay, so now let's work backwards. I'm going to subtract off 4 seconds because there's a 4-second gap here. And the gazelle runs 73 feet every second. So 4 times 73 is what I'm going to subtract off. 1760 minus this number in red is 1,468. And I do the same thing here. Another 4 times 73. I'm down to this far now. But notice, right here the gazelle and the cheetah are at exactly the same point. But here the gazelle is ahead of the cheetah. Here the gazelle is even farther ahead of the cheetah. You can almost imagine the cheetah catching up to the gazelle as you look at the numbers. And so here, again, each time it's 4 times 73. Here it's at the 4th second, the gazelle is way ahead, almost 600 feet. The cheetah is more like around 350 feet away from where it started. So the gazelle's got a nice lead right now. It's looking good early along for the gazelle. Now again, my table's kind of screwy because from here I go down by 2s instead. Whoops, the wrong way. So this time I subtract off 2 times 73 each time. But the point is, if I do that, what I find here is that the gazelle, when it starts, is 300 feet away from the cheetah. So that's the answer to the question, how far away from the cheetah does the gazelle need to stay for it to be safe? Well, a little bit more than 300 feet, or literally 301 feet if the cheetah really runs exactly at the speed as it says here. So that's how far apart they need to stay, 301 feet. The textbook, as I said, did this a different way. The textbook shows you this graph, And you'll find this in chapter 3.5, and it shows that the gazelle is 300 feet away from the cheetah when they start, and after 20 seconds, the two of them have caught up with each other, which is bad news for the gazelle, great news for the hungry cheetah. But the textbook found this number 300 a different way. The textbook used the algebra technique that I'm going to talk with you about in class next time. First of all, it gave itself a picture. This is this safety zone, how far apart the gazelle and the cheetah need to be. They need to be X feet apart for the cheetah to be safe, the gazelle to be safe. So the gazelle is going to go 73 times 20 plus some distance X. And that's what they have here. They set that equal to the cheetah's speed distance, speed and time. 88 feet per second times 20 seconds. And if you solve this problem, 73 times 20 plus x is equal to 88 times 20, and you should be able to solve a problem like this, you would have found that x is that 300 feet that we've been talking about. So when we get back together in class, I'm going to talk about this algebraic method for figuring out when two different moving ideas or things end up meeting and matching, like the moving cheetah and the moving gazelle, or the moving temperatures of the two cities in the previous problem. That's it for this lesson. I'll see you in class.